so the first problem here is to prove that the roots of a polynomial in the complex plane depend continuously on the coefficients. Sounds very true. So maybe some of you just know the proof from before. I prefer it. Let me get some suggestions from those who came up with something right now. Does anybody have a suggestion how we might prove it? I know two different ways to prove it. One is completely elementary, and one uses something about integration in the complex plane. Does somebody want to suggest an idea?
Well, did anyone come up with a proof that does not use contour integrals?
Piyush?
I mean, SLT does not use contour integration. We just use the definition of continuity.
Well, okay.
So if the root is not, so assume that the root is not a continuous function. So that means that there must exist a neighborhood of the coefficients in which, so that you can perturb to that neighborhood.
Would you like to come up here, or no? Yeah, so we have to use the definition at some point. Yeah, I agree. We can do it together on the board. See? So you're saying there's an elementary proof which doesn't use anything. Okay, yeah, that's nice. Because I think this proof is not widely known. And I mean, you can do it. Yeah, you can do it.
So that not be a root of. Suppose, so this is a function, Z naught. Suppose Z naught is not a continuous. Does it mean that there exists some epsilon zero such that some perturbation of this such that
So we have an n-tuple of roots, right? I guess maybe we have to be a little bit
yes,
careful. So
yes, just one root, and that root is a continuous function.
you're claiming that you can somehow identify n labeled roots, and each of them moves continuously. Yeah.
So yes, so such that
So you mean like the roots are distinct?
yeah, I'm assuming that the roots are distinct.
It's a little bit tricky if you,
Huh?
we might have multiple roots.
Yeah, but that's
But I guess it's safe to say that if, the contrapositive is that there's a root of this polynomial, then we have a sequence of polynomials that coefficient-wise converge to that, and in that sequence, we can choose maybe a subsequence such that they don't have any root in the vicinity of some particular root of P. Yeah. So that should be our starting point.
Yeah. So that's what it is. And so they're saying that the value of the polynomial is continuous. So there exists some neighborhood. So there exists a neighborhood.
Let's draw a picture here. So draw some illustration. So we have some sequence of. So what is Q?
So Q is just one direction. So
Okay. Okay. Yeah.
So we're saying that's what this means. And this will be a contradiction because of the following fact that the value of the polynomial, so the polynomial itself is continuous. And the fact that there are no roots of this polynomial means that its value is at least some epsilon to the n. Delta to the n, or something like that.
So you're using something interesting now.
I'm using that it has and all the rest.
So yeah, what exactly is this statement?
Yeah, so I'm using that, but Px, epsilon Px factorize this as this is the original thing was minus, but doesn't matter. So just factorize that something like P.
Oh, why is that true? Wait a second. So, so yi are the roots of what?
This one. So fix an epsilon.
Yeah.
So it's a function of epsilon.
They depend on epsilon. Yeah.
But all, I know that all of them are at least delta away from zero for every epsilon positive. And yeah, so now this should be a contradiction because this means that the value at z naught of this polynomial is always at least delta to the n times this number. So
Why did you get this? What,
oh, this is just to make it monic.
yeah. So you're saying that the value
Yes, so now this means
of
that
for every epsilon.
therefore the Ez naught, therefore Ez naught, epsilon Ez naught is at least the value of kn plus epsilon dn times and this is true for every epsilon. But that's a contradiction to the fact that this so as epsilon goes
Leave
to
delta. Okay.
delta was fixed. And,
Yes. Yeah, I think I'm okay with this. Did everybody follow? I want to do it a little bit differently, but
so yeah,
I guess
you
yeah.
assumption that an is not equal to 0 under root.
Yeah. So the fact about polynomials that you use is that if the roots are at least some distance from the roots of the other polynomial, then the value
I think this will be said.
value at those roots is at least something, and therefore in the limit it cannot be 0. And this delta does not depend. This delta doesn't depend on epsilon. That's the interesting. Sharon and Nikhil, the jury is jury satisfied. Yeah. Let me.
Some of the zeros could be close. Like 1 or 2, 1 0 could be off, right? So
what if-
assume that for all I you have this, but you should just assume that this should just be.
Well, you should. I guess you should make this circle small enough. Is that your point? That even the other roots.
To get a contradiction is just that 1 doesn't move, doesn't stay close, right? But in his contradiction, it's he assumes that for all
Yeah,
i's, right?
so here the so the fact
he's-
that
So the other roots are somewhere far away. He's evaluating at a point x.
If it's the case that for every delta there is a root in that vicinity, then that is continued. Yes, so this is a red herring.
So you're not. No, that's a valid. Yeah, if you have an objection, then certainly raise it. Yeah.
Yes, no, so I think the objection is because I'm thinking of the root as a function, but that's not quite right. I mean, what one is actually arguing is that there is this z0 which is a root, and then you have this thing that the fact that it's not continuous is saying that that there is a neighborhood of that point such that you will have no roots in the neighborhood. If you have other roots coming into the neighborhood, then that's like saying that it is continuous. I mean, it's not identifying roots.
Yeah, you're saying the roots don't have names. The thing
Yeah,
that's
yeah.
continuous is the number of roots.
Yeah.
that there's.
So that's what the contour would be.
Yeah.
Yeah.
Can't we just take the contour integral?
Yeah.
Oh, contour integral. Okay.
It's continuous because integrals are.
Yes. Yes. Do you want to? Yeah. Actually the textbook proof that probably people know is using a contour integral. Maybe we should present that too. Would you like to volunteer?
Try.
Sasha.
Right, so that must be the number of roots with multiplicity, right?
That's 2
Well, yeah.
Yeah.
That's it, right? So that's continuous.
Yeah. Root number of roots inside the
Inside
curve.
this, the contour. So if that's continuous, the integrals are. That's why we like them.
Yeah.
So the number of roots with multiplicity stays inside. It's inside it. Any small contour stays.
Yeah. It's.
Sorry.
Yeah. Thank you very much. Okay. Everybody happy, or does anybody have a different proof? Very basic fact, but we all forgot these things. At least me. So the second exercise is about the Hermite-Sylvester theorem. So we have this matrix for polynomial. Polynomial P. Power sums, mk is the summation of the roots power of k. And we call this matrix Hij, where we put the power sum for a plus j minus 2. Okay, and I and j is between 1 and n. So, like this. So, now we should prove something about h being positive semi-definite. So let's first, let me do that for you because it's obvious what you should do first. Let's look at what this expression actually means. X transpose hx.
But that's the solution that you're...
No, I mean, one direction is easy. I think one direction is a little bit, if you have an obvious solution for both directions, I'll be happy to see it. But you have to do something, I think, in one direction. Right?
Meaning that if it's not, then there is a complex root.
Yeah. If it's not real rooted, then you have to show that this can be negative. You have to do something. Yeah, this one direction is pretty clear, so I'm not going to force anybody to go to the board for that. Let me do it first. So what is this expression? Okay, xi, xj. So this is a summation of the roots to the power of a plus j minus 2. Let's call the summation index L. So it's a summation over L. Summation over I, xi, lambda L to the, here I do like this, I minus 1, summation over j, xj, lambda L to the j minus 1, right? Yeah, so this is the quadratic form. So one direction is really easy, because if the roots are real, then for x real, this is something squared, something real squared, so it's certainly non-negative, right? That's what I meant by the easy direction. So the other direction was not completely obvious to me at first. If you have a polynomial which is not real rooted, how do you find a vector x such that this is negative? Any suggestions? So let me write this. I'm not doing anything. I will not do anything non-trivial for you. I will just write this as summation over L, some polynomial, let's call it Q of lambda L squared. So Q is some polynomial whose coefficients we can design. Xj lambda to the j. One thing about Q is that I'm only allowed to use degree n minus 1 actually, because this is an n by n matrix and the powers only go up to n minus 1. So you have to be a little bit careful about the degree. So the question is, summarize the question, given px with some complex roots, not real roots, come up with
Right.
Q.
Yeah, you do interpolation, right? So you make
Okay.
it 0 except into complex conjugate.
Yeah, so the roots are, yeah, I should say, maybe I didn't say that, but we assume that the polynomial has real coefficients, okay? So complex roots form complex conjugate pairs. Yes, please. Sorry, I interrupted.
Right, so you do. So there are n minus 2 roots where you make it 0.
Uh-huh.
And there is a pair of complex conjugate where you make it nasty, right? So that.
Yeah, that's how I would do it. Yeah, actually, I don't know. I couldn't find the proof online. I was preparing the slides, so yes.
easiest to see if you factor the matrix H as a product of a Vandermonde matrix times its transpose.
Oh, so that's a different way. Okay,
And I
so
think you see the
I'll let you do that next if you want. Let's finish this argument because, yeah, that might be nice too. So, yeah, so Sasha is suggesting, I think, what my intended solution was, which is basically use the roots of P. So assume the roots of P are, so there's some complex conjugate pair, lambda, let's say lambda 1 conjugate, and then some other stuff. Let's call this lambda 3 and so on. So we form polynomial Q. Q of z is the product over all these other roots, right? We should be careful if the same conjugate pair appears multiple times, but let's ignore that. I think it's not an issue, but the formula would be a little bit. So we take a product.
Yeah, it's not an issue why previously the proof continued.
Maybe I think you can do it directly, but yeah, let's ignore that. So we have this, and then we have to add some stuff here, which let me call it az plus b, which basically is designed to move this conjugate pair to plus minus I, right? So we can find, choose A, B real. Can everybody see that? Is it okay? Or too low? Choose A, B real such that A lambda 1 plus B is plus I, A lambda 1 conjugate plus B is minus I. So you can do that. In the complex plane, we have some complex conjugate pair, so just map it to plus minus I by a linear function. Just scale it so that you get the imaginary component is plus minus 1, and then make the real component 0. So we can do that, right? Now, if you plug in any of these roots, starting from lambda 3, if you plug in anything into Q, you get 0, because this will disappear. Okay, so for any L starting from 3, Q evaluated at lambda L is 0, clearly, because of that product. And Q lambda, actually, sorry. So I wanted to design this to be the value of the polynomial to be equal to plus minus I, which I can also do. So the value of Q evaluated at lambda 1 or lambda 1 conjugate should be plus minus I. If I plug in lambda 1 or lambda 1 conjugate into this, I get some complex conjugate pair. So I can adjust the coefficients here to make the value plus minus I. Does everybody believe that? No? I have some conjugate pair, so I can this is some non-trivial complex conjugate pair, so I can scale it. I can move them along some line to hit the imaginary axis somewhere. I choose this linear function so that it becomes plus minus something imaginary. Then I just scale it to make it plus minus I. Yeah, this is supposed to be an interactive session. Do you agree or not? Or maybe there's an easier way to say it. Yeah, Nikhil?
So
You're just using, you have these n-1 degrees of freedom.
But you have to keep it real values.
Yeah, but
Or is maybe
so I have a complex conjugate pair. You know, I multiply them by z. For z, I plug in lambda 1 conjugate. This is some non-trivial complex conjugate pair. So I will get these 2 points and some other complex conjugate pair in the plane. It's not just, the only thing I need about these 2 pairs is that they are not just a real multiple of each other. It's not like that. I have 2, let's call them non-trivial pair of complex conjugate pairs. So then I can combine them by a linear combination somehow to get a pure imaginary pair.
Can't you just shift away the real part? Just apply shift to the polynomial? Would that work?
I don't want to shift the polynomial because when I plug in the other roots, it should be 0. So I don't want to just shift the polynomial, I want to multiply it by something. I claim I can multiply it by a linear factor with real coefficients such that I cancel out the real part after plugging in lambda 1, and I get a pure imaginary pair plus minus I. Yeah, agree. Sasha agrees, and that's it. So, so I have the property that q of lambda 1 equals minus q of lambda 1 conjugate. This is I. This is plus minus I. So I have this quadratic form where if I plug in any root except for the first pair, I get 0. So this is all 0 except plus I squared plus minus I squared. So it's actually minus 2. So I produced a vector which gives me minus 2. Good? I don't know. That's my solution. And there's apparently another solution, which if you want, same. But it's not using something about positive semi-infinite matrices rather than polynomials. So maybe, if you like, you can give it.
Maybe you're just saying that if you factor H as product of Vandermonde, then the quadratic form is literally what you wrote, the sum of Q lambda L squared.
Okay, I don't know. I would still like to see it if you want to write it down. We have 5 minutes.
I'm not saying anything. It's
Sure.
already. So I'm just think you can read this as so that what are the roots lambdas? Okay. So take the Vandermonde matrix 1 lambda 1 squared 2. The degree is n. So this says here up to some indices that H is, can anybody still see this? Is V transpose V, right? Multiply it out, you get exactly the Hermite matrix if you multiply these Vandermonde matrices, but now you can simply diagonalize the quadratic form, which is essentially written here. It's a sum of squares of linear forms. So the question is, what is sort of the signature of this matrix? So if the root is real, then we have a real square here. So that's nice. We want to diagonalize over the roots. But if you have a complex conjugate pair, then, or a complex root, then this is a complex linear form. That's not so nice. But its complex conjugate pair will show up also. So the thing you have to think about is what happens if you add, you have this linear form squared. Maybe call it something. But let me do it for 2. So there's, take this linear form. So this is I take a complex number alpha, suppose it's one of the rows of my matrix. So I will have alpha to the I xi is my linear form. So I take one of the rows of V and multiply it. That's also the thing for the complex conjugate root. So the question, I think, is what is this? that is sort of, you multiply things out, it's sort of the real part squared, right, the linear form. And by that I mean take real part coefficient ones. And I'm missing something, like a 2. An imaginary part. So this is sort of diagonalized over the reals. These are now real linear forms, and this has a positive eigenvalue and a negative eigenvalue. So for every complex conjugate pair of roots, you actually get a positive and a negative eigenvalue. You can be even more precise. The signature of the Hermite matrix counts the number of real roots. And so if it's PSD, then all of the eigenvalues are non-negative, so you count it. You only have real roots. So you can even count the number. If you have complex roots, you can count the number of real roots, because complex roots sort of disappear in the signature because they contribute a positive and a negative eigenvalue.
Okay, nice. Any questions or any other comments?
There should be a 2. It's not 1.
Thank you. All right, so I guess we should finish. If there are no other comments. 9:50 we were supposed to finish. Yeah, all right, good.